Thank you for the nice introduction. I would like to talk about my joint work with Man-Kwun, Chiu and Wolfgang Mulzer, which concerns the alpha ham sandwich theorem. So let us look at the definition of this thing. So we have d point sets in d-dimensional Euclidean space, which we also regard as different colors, and we are given some vector of integers where alpha I is at least 1 and at most the size of pi. And the natural question to ask is there a hyperplane that has some orientation such that the positive half space contains precisely alpha I points of pi for all I? Like an example, here we have green point and violet points, and this oriented line contains 3 green points and 4 violet points. We can of course draw many other hyperplanes which realize different alphas. However, if we move the points a little bit to get something like this, then no matter how hard we try, we cannot find a line which contains precisely 1 green point and 1 violet point on one side. So the answer to the above question is true, but only under certain conditions, which was shown by Steiger and Zhao in 2010. Previously, there was also a continuous version of this theorem. This seems very much like a generalization of the classical ham sandwich theorems where we only worry about bisections, but it will become shortly clear that this is not true. This is an example from before. So we say that a point set is colorful if it contains 1 point from each color, and a hyperplane is colorful if it is incident to a colorful set. For instance, this green point and this violet point forms a colorful set, and this hyperplane, by virtue of passing through these 2 points, is also colorful. We will only be interested in solutions which are colorful hyperplanes, that is also colorful sets, because it is easy to define orientation for such point sets. So the first condition is that the point sets must not look something like this, but that they should be well separated. What this means is that for any subset of colors, the points of that color should be strictly separated from all the other points by a hyperplane. This is unfortunately very expensive to verify, but there is a short certificate that witnesses this violation. It is simply a partition of the colors that is not well separated. There is one more condition which is illustrated by this example here. So we can have many colorful sets. We define this line which contains 4 green points and 2 violet points. However, if instead I want only 1 violet point and 3 green points, then there is no solution. In fact, the point sets must follow some weak version of general position. This is also quite expensive to verify, similar to the well separation property, but there is a short certificate of violation, simply a subset of d plus 1 points of affine dimension d minus 1. In fact, the condition that they must be of d colors is what makes this a weak general position. So Steiger and Zhao showed that if the point sets follow these assumptions, then for every alpha vector there is a unique hyperplane which is colorful and has an orientation, and it divides the colors in the prescribed ratio. Naturally, the number of colorful sets is the product of the cardinalities of all the sets, all the colors. That is also the number of colorful hyperplanes, and indeed it is also the number of choices of alpha vectors. And the theorem shows that there is a bijection between the alpha vectors and the colorful hyperplanes. We also saw that if any of these conditions are not true, then for some alpha you might not have a solution. This also implies that for some alpha there can be multiple solutions. In real life, if we have a ham sandwich, it is not well separated, even though it might follow some kind of general position. So although we might be able to bisect it, we might not be able to cut it in any arbitrary ratio. Steiger and Zhao also gave an algorithm that takes that much time to compute a dividing hyperplane if all the conditions are true, which was later improved to be linear in n but exponential in d. And our aim is to find the precise computational complexity of this problem. So we know that under the promise of these two conditions, there is always a solution for every alpha vector. However, the promise is very expensive to verify. So it makes sense to turn this into a non-promise problem, a problem where there is no assumptions on the input point set. And this can be achieved by allowing some more outputs. So instead of having just dividing hyperplane as an output, we also allow for certificates that witness violations of weak general position or well separation. Indeed, G1 is what we are looking for, and GV1 and GV2 are violations which tell us that the assumptions were not true. The theorem says that if none of the violations hold, then G1 must be true, there must be a G1 solution, otherwise there must be one of the violation solutions. So this is a total search problem lying in the complexity class TF and P. We can make a more precise classification of this problem. So this picture contains many complexity classes. What is already known and quite obvious is that ham sandwich lies in PPA, while we show that alpha ham sandwich lies in this complexity class, which is supposedly smaller. This is our result. So the name of this class is UEOPL. What does this stand for? That becomes more clear when we look at the problem that defines this class. So the input is a graph which consists of a path and perhaps some isolated vertices. More formally, the path is called a line because each vertex has in degree and out degree at most one, and there is a potential for each vertex that increases when we walk along the line. Also in the input is one vertex which is the source, which is the start of the line. Naturally, there is a unique end to this line, and the goal is to report this end of a line. This complexity class was introduced last year at iCalc. Now the problem seems quite benign, just report an end of a line solution, but it is more difficult than that because the graph is not given explicitly but implicitly using some Boolean circuit. These circuits compute the neighbors and the potential value for each vertex, and each vertex is encoded as an n-bit input to the circuits. These circuits use a polynomial number of gates, and the graph contains exponential number of vertices. That means it's quite inefficient to verify if the circuits indeed define a path graph. To handle this, apart from the end of line solution, we also allow for violation solutions. That means if we have examples like potential not increasing along a line or multiple lines, then we can report some certificates that witness these violations. This makes it a total search problem and defines the class UEOPL, which contains problems reducible to this unique EOPL problem. Let us now see why we can have a redirection from alpha ham sandwich to unique EOPL. Suppose we have 2 point sets in the plane, orange and green, which are well separated and in weak general position, and our goal is to find a line that contains 3 green points and 3 orange points above it. And suppose we are also given a tangent hyperplane. What I want to do is that I want to increase the alpha for the orange points first until it reaches 3, and then I want to increase alpha for the green points. So I pick this point, make it an anchor. Additionally, I create a vertex which represents this hyperplane. I now rotate the hyperplane around this anchor. I have increased alpha for the orange points by 1, and this hyperplane is represented as a new vertex. This rotation is represented as an edge. We continue the rotation to get a non-colorful hyperplane. This time, if we continue the rotation, then alpha would increase for the green point, which we don't want yet. So we switch the anchor and then we continue the rotation. Eventually we reach this hyperplane, realizing alpha for the orange points. Now it's time to switch the anchors and rotate so that alpha for the green points increases. We continue this rotation, swapping anchors whenever we have non-colorful hyperplanes. Eventually we reach our goal. So we have gone from this vertex, this hyperplane, to the solution hyperplane by a series of local changes, which is equivalent to walking along this path in the graph, which looks like a line. You are given the source and you want to find the thing. More generally, this defines a graph which looks very much like a grid graph. You are given a vertex representing the tangent hyperplane, and by walking on a path starting at that vertex, we can reach the target vertex. All of the vertices are self-isolated. The problem becomes more interesting when there are violations. For example, here the green and the orange points are not well separated. And then if I rotate from h1 to h2, I see that the alpha vector goes from 4,3 to 2,2, which is unexpected. It should have increased in one of the components or decreased in one of the components. Indeed, they don't form an edge in the graph, but the path ends at h1 abruptly. There's another example where you have two hyperplanes that have the same alpha vector and they represent two distinct lines in the graph. Our main technical contribution is to show a polynomial time reduction from alpha ham sandwich to unique EOPL. This also shows that this problem is weaker than the ham sandwich problem, which was not known before. The next thing to consider is that ham sandwich is complete for PPA. Is there a corresponding result for alpha ham sandwich in UEOPL? Or perhaps more optimistically, is alpha ham sandwich in the complexity class P? Thank you.